So this is our last lecture on frequency response. We'll look at the cascode, the telescopic cascode and the differential amplifier configurations. This lecture will only look at qualitative analysis of frequency response. We will not derive any equations. Whatever equations should be derived, I am leaving it to you to derive. We'll just kind of study the time constants and see how on which time constants dominate the frequency response. Alright, so let's begin with a telescopic cascode. So this is the first circuit we had looked at when we started looking at the telescopic cascode. So we say we have two NMOS transistors. The first is a common source stage and the output is connected to a common gate stage. And in this case, I've put a current source as the load. We need to study this circuit for frequency response for two different load configurations. One is a single PMOS or just a resistive load. The other is a cascode PMOS load. Alright, in fact, we had looked at both of them earlier when we were doing the low frequency analysis. Now we'll look at both of them for high frequency analysis. So let's begin with the single PMOS load. Now, as we had seen earlier in lecture 16, this circuit, when the output is taken here at VO, has a gain of about GM1 RO3. Alright, perhaps I hope you remember. So the gain of this circuit, the low frequency gain, is basically GM1 times the R out, looking at the output node. And the R out of this circuit, looking at this node, is RO3 in parallel with GM2 RO2 RO1. And GM2 RO2 RO1 is typically much greater than RO3, and therefore RO3 only stays, and therefore the gain is GM1 RO3 approximately, minus of course. And when we had studied these at that time, we had said that, well, this gain is the same as the common source amplifier, so that this doesn't make sense as a high gain amplifier. But now let us look at the frequency response of this circuit, and we'll find that okay, let us first look at it. Okay, so the gain from Vin to VO1 of this circuit is minus GM1 into the resistance at this node, right, approximately. And the resistance at this node is R down in parallel with R up. And R down is of course RO1. R up, as we have seen before, the resistance looking up the source of a MOSFET is RO2 plus RO3 divided by 1 plus GM2 RO2. Right, so we say this gain VO1 by Vin, VO1 is here, by Vin is minus GM1 into RO1 parallel RO2 plus RO3 by 1 plus GM2 RO2. Now if we assume that RO2 and RO3 are equal just for the sake of simplification, then this becomes 2 RO2 by GM2 RO2, ROs cancel, 2 by GM, which is much less than RO, and therefore we get this gain to be minus 2 GM1 by GM2. Basically a ratio of 2 GMs. And the ratio of 2 GMs is typically of the order of 1. In fact, especially if both of them are NMOSes connected in a cascode. So this gain is basically small, 2 or so, roughly around 2. Now what this means is that the Miller capacitance due to CGD1 is going to be small because the gain from the gate to drain of M1 is small. This is the advantage of this circuit compared to a common source stage. Because a common source stage has a large gain and therefore a large Miller capacitance. This circuit has a small Miller capacitance but the same gain as a common source stage, right? So by adding a transistor, we have improved the frequency response while keeping the low frequency voltage gain the same. In fact, let's also look at the time constant here, right? Here, the time constant is the capacitance times the resistance. And the resistance, as we just saw, is basically RO3. So that time constant is also basically the same order of magnitude as the output time constant of a common source amplifier. So that is the advantage of this circuit. It gives a better frequency response compared to the simple M1, M3 common source amplifier. So this circuit is actually used in RF circuits where high frequencies, you want a 3 dB frequency to be very high. Alright, we leave it at that because we are not going to discuss RF much in this course, but that is this illustrates the use of this circuit. Alright, now let us look at our standard telescopic cascode with a cascode PMOS load. So again, what we'll do is we'll look at the time constants at each node and basically figure out which time constant dominates the frequency response or the 3 dB minus 3 dB frequency of this circuit. So there are 1, 2, 3, 4 nodes. Actually this node and this node, as you can see, there is a kind of a symmetry. So the time constants at these two nodes are going to be similar to each other, not the same, because usually the PMOSs are larger and so the capacitances at this node are larger, but the same order of magnitude. So we say at VO1 and then similarly at the drain of M4, the resistance seen is about RO. How is that? So looking down again is RO1, looking up is how much? You think about it, it will turn out to be about RO. Alright, we've seen this before. In any case, so what will it be? It will be RO2 plus the resistance looking up divided by 1 plus GM2 RO2. This looking up is GM RO squared. So you'll get RO2 plus GM RO squared divided by 1 plus GM RO. So it is if approximately GM RO squared by GM RO, which is RO. So the resistance at this node is basically RO by 2 actually. I've said RO, so the order of RO. And the capacitance is actually, what is the capacitance here? CGS plus CSB plus CGD plus CDB, 4 capacitances. Similarly here also 4 capacitances, CGS plus CSB plus CDB plus CGD. Number of capacitance is the same. As I said, this is likely to be larger because PMOSFETs are larger in size typically. So that is the order of the time constant at VO1. Let's look at the gate of M1. The gate of M1 of course sees the Miller capacitance. And the gain in this circuit from Vin to VO1 is of the order of minus GM1 RO. Alright, the earlier circuit with only M3 and no M4 was minus GM1 by GM3. This is minus GM1 RO because the resistance now is RO by 2 actually. So this should be minus GM1 RO by 2. So this gain is about the same magnitude as a common source amplifier. So the Miller capacitance here is large. Typically RG is not large because for RG to be large in a cascode, the previous stage to which this cascode is connected will also have to be a cascode, but it is rare. I have actually never seen a cascode cascaded with another cascode. The frequency response is just not good enough, so these are hardly ever used in practice. Therefore RG is typically not large. So what we say is the time constant at this node is larger than the time constant at this node. Let us just conclude that and move forward. At the output node, so let's go to the output node. At the output node, we know the resistance is large. It is of the order of GM Rho squared by 2. And so that is a very large resistance. The capacitance is of the same order as at VO1 and the drain of M4, but the resistance is very large. Typically, therefore, in a telescopic cascode, the output time constant, because of the very large Rho, that output time constant dominates the dominant pole, right? The dominant pole, as you know, is basically 1 over the sum of all the time constants. The time constant at the output node dominates, and that is because of the large R out. The second dominant time constant will be either at the gate of M1 or at the drain of M1, and that depends on the value of Rg. It is difficult to make a generalized statement about which time constant will dominate. Alright, so generally if to find the 3 dB minus 3 dB frequency of a cascode, one just looks at the output node. In fact, this is what you had done for the third assignment. Alright, so as I said at the beginning, this derivation of this complete transfer function of a cascode is tedious. It is 3 nodes. It is very, very tedious. It is one of the most complex transfer functions you will encounter in this course. We will not derive it. I think you should derive it in your own time, because it is a really, really nice exercise to learn meticulousness and patience, because you have to do it very, very carefully, very, very slowly, not make mistakes, and the equations become very big. Alright, so please do it. It is a good exercise. Okay, so that is the telescopic cascode. Let us look at the differential amplifier. So here is a differential amplifier. We have added Rg for the sake of generality. The first question we ask is, okay, so we want to study the frequency response of the differential amplifier. How do we even begin to find the frequency response? Alright, perhaps it is an interesting question. The answer is actually simple, but you are given a circuit and you are asked, well, find the frequency response of this circuit. That one must first answer, how do we begin? Alright, and of course the answer is that we do this for two different sets of inputs, as we did for the low frequency case. So we find the frequency response for differential mode inputs and then for common mode inputs. And then if we want to find any the frequency response for any arbitrary inputs, then we do a linear combination of the differential input frequency response and the common mode input frequency response. Again, we will not derive, well, we'll see what we'll do. Alright, so let us look at the frequency response of a differential amplifier, first for differential inputs and then for common mode inputs. So for differential inputs, we say V in 1 is equal to minus V in 2 equal to Vd by 2. The small signal inputs are equal and of magnitude opposite in sign. Now we had discussed earlier for low frequency that when the inputs are equal in magnitude and opposite in sign, then the source terminal of the differential pair is at virtual ground. Basically it is at zero potential, and because it is at zero potential, the circuit basically reduces to a common source configuration. Now the same thing holds even if the frequency is high, because the symmetry or the anti-symmetry is not disturbed by the presence of capacitance. So the virtual ground still holds, the source terminal is still at zero AC potential, and therefore the circuit reduces to a common source amplifier even for high frequency analysis. As a result, for differential inputs, the frequency response of a differential amplifier is identical to the frequency response of a common source amplifier, and that we have studied. Therefore, we don't need to study it again. We just go back and look at a common source amplifier. So this is why we don't need to derive the transfer function For a differential input, we've already derived it. Okay, let's look at common mode inputs. For this we will not derive, we'll just do a qualitative analysis. Okay, so for common mode input, these are equal. V in 1 is equal to V in 2 equal to some Vc. What we do is we make the circuit completely symmetric by cutting, or I should not say cutting, dividing the tail transistor, which is usually M5, into two parallel transistors of width half of M5. Alright, if you think about it, two parallel transistors of width W by 2 and W by 2 is identical, and it is the same as one transistor of width W. Alright, so this is the same as one transistor of width W. Now, if we cut this right in the middle, then no current flows across any horizontal wire, and therefore we can look at only one half, the left half or the right half of the circuit, to determine the frequency response of this circuit. Earlier when we did low frequency, I had done RO5, right? We had done in fact 2 RO5 here and 2 RO5 here. So how is that 2 and this is divided by 2? Because if the width is half, the resistance is double. Alright, but now we are saying transistor, not resistor, because we have to account for the capacitances also of the tail current transistor. So that's why we divide this circuit with the transistor itself. And now we draw the small signal circuit for one half of the differential amplifier. So this is the half small signal circuit for half of the amplifier. So this is M1. M3, so 2 RO5 here, but there is a capacitance. So I have combined this as C2, C3. So C3 will be a bunch of capacitances put together. You should sit and write C3 as the sum of actual capacitances. Similarly, C2. And there is CGS1 and CGD1. Alright, so now we have three nodes. This node, and this node. Let us look at the time constants of the three nodes to kind of draw some very qualitative conclusions about this circuit. Alright, so we look at the time constants, actually not the three nodes, but the four capacitances is what we'll do. I'm sorry, not nodes. The time constants associated with each capacitance. So in CGS1 we look at, so in fact, so this circuit is a common source amplifier with source degeneration, as we have seen multiple times before. And so from the gate to the source, this is just a source follower, and the gate through the drain is a common source amplifier with source degeneration. Now because gate to source is a source follower, the voltage, the AC voltage gain from the gate node to the source node is roughly 1. Alright, the source follower, if it is about 0.7, which is more realistic if we include the GMB of M1. But in any case, let us say that for now we'll consider this to be 1. If this is 1, that means that if this is VG and this is VS, then VG and VS are approximately equal in the AC circuit. This is now AC analysis. If VG and VS are equal, that means that there is hardly any current flowing through CGS1 because VG, the voltage across it is 0. The voltage across CGS1 is VG minus VS. VG is equal to VS, so the voltage is 0. Therefore, very little current, AC current, flows through CGS1, and therefore it has a very little impact on the frequency response of this circuit. So we'll just ignore it. Qualitatively again, quantitatively, we actually did this last time in the last lecture for the source follower configuration, which is more accurate, but right now we'll not do a more accurate discussion. Okay, CGD1 is this one. Now because this is again a circuit with source degeneration, the voltage gain VO1 by Vc is roughly minus RO3 by 2 RO5, right? In fact, that is a common mode gain, right, of this circuit. And the common mode gain is of course small. If it is typically of the order of 1, it of course depends on the actual values of RO3 and RO5, but let us assume it is 1. So the gain from Vg to VO1 is 1. Therefore, the Miller capacitance due to CGD1 is small. Alright, CGD1 is already small and it is getting multiplied only by about 1. This is minus 1 actually. And so when reflected to the input, the Miller capacitance is small. So the time constant associated with the Miller capacitance is also small because Rg is typically not very big. So alright, so CGD1 contributes minimally, CGS1 contributes minimally to the total time constant. What is the resistance seen by C2? C2 is this one. What is the resistance? Just think for a minute before continuing, or pause and think and continue. Okay, so C2 is if R2 is a resistance seen by C2, then that is a resistance looking into the output of this circuit. So it is RO3 in parallel with the resistance looking down, which is GM1 RO1 times 2 RO5, and that is approximately equal to RO3. And so the output time constant is RO3 times C2. Alright, and this is about the same time constant as the output time constant for the differential mode circuit, because there the resistance was RO, in fact that was RO3 parallel RO1, so that time constant was slightly smaller. This is a factor of 2 larger than the small differential mode circuit. Okay, what about the resistance seen by C3? What is the resistance seen by C3? Now we've done all this before, so you should be able to just look at it and say what it is. So let's look at it. So it is the resistance seen by C3 is 2 RO5 looking down, and looking up it is RO1 plus RO3 divided by 1 plus GM1 RO1. Alright, so R2 RO5, all that. If ROs are equal, this is 2 by GM1. 2 by GM1 is much larger than 2 RO5, so this is approximately 2 by GM1. So this resistance is small. This resistance seen by C3 is small compared to the resistance seen by C2. Therefore, of all the 4 time constants, the time constant corresponding to C2 dominates, and so this is the minus 3 dB frequency. So the minus 3 dB frequency of the common mode response of a differential amplifier is basically approximately 1 by R2C2. Alright. Now let us look at something else. It is very interesting and very, very important. C3, this also creates a 0 in the transfer function. I'm not doing this mathematically, but let us look at this qualitatively. So let me go back. Where were we? The gain, this one. The okay, no, it's not here, I'm sorry. Let's do here only. Okay. So we know that the gain from gate to VO1 is of the about minus RO3 by 2 RO5. Alright, that is for low frequency. So RO3 divided by 2 RO5. The resistance looking up from the drain divided by the resistance looking down from the source. We've derived this earlier. So that is the voltage gain. Now that was for low frequencies. For high frequencies, the resistance looking up from the drain is still RO3. But now the impedance looking down from the source is 2 RO5 in parallel with 1 over j omega C3. Alright, so the gain, the common mode gain of this stage at high frequencies, VO1 by VC at high frequencies can roughly be written as RO3 over Z, where Z is the parallel combination of 2RO5 and 1 over j omega C3. Now what happens as frequency increases, as omega increases, 1 over j omega C3 becomes smaller. Omega becomes larger, 1 over j omega C3 becomes smaller. Therefore, for the parallel combination of RO5 and 1 over j omega C3, as frequency increases, the impedance due to C3 dominates, and the overall impedance Z, its magnitude decreases as omega increases. As the magnitude of Z decreases, the gain, the common mode gain of the stage increases. Alright, omega increases, 1 over j omega C3 decreases, Z decreases, gain increases. Alright, this is a very important phenomenon that has to be very carefully monitored while designing differential amplifiers. Basically, the common mode, we want to keep the common mode gain as small as possible so that the CMRR is large and so that common mode signals are rejected at the output of the differential amplifier. But as frequency increases, the common mode gain actually increases, and that degrades the overall performance of the differential amplifier. So here is a representative plot of the blue is the common mode gain. This is a Bode plot of the common mode gain is blue, red is blue is the differential mode gain, it is high at low frequencies, red is the common mode gain, and green is the CMRR. So at low frequencies, of course, the common differential mode gain is large, the common mode gain is small, CMRR is large, about 30 dB. At about the same frequency, you can see this, you can see that the minus 3 dB frequency of the common mode is slightly smaller than the minus 3 dB frequency of the differential mode, because as we just saw a few minutes ago, this time constant is about twice this time constant, and therefore the frequency is about half of this. So you can see that here. And then so there's the both start falling at 20 dB per decade. And so the CMRR increases a little, but not a big deal. It is still very, very high. But here, the zero occurs of the common mode gain. The common mode gain encounters a zero, and so the gain stops falling. Alright? The differential mode gain is falling. The common mode gain has become constant. Alright? So what happened? As this becomes a short circuit, the common mode gain becomes larger, and so the common mode gain is become increasing. Alright, so the effect here is there is a pole that is causing the common mode gain to drop, but this zero is preventing it from dropping, so that the overall effect is that the gain is somewhat constant. Then of course another pole is encountered, and so the common mode gain starts falling. But what we see is that the CMRR, which we want to be high, is becoming lower at high frequencies, and in fact it becomes 0 dB, which is 1 at very high frequencies. CMRR 1 is of course not at all good. What this means is of course that the common mode gain and the differential mode gain are the same. This is a very poor response for a differential amplifier. So what one has to be careful while designing such a differential amplifier is that this zero occurs at a high enough frequency so that all amplifiers have a frequency up to which, and so typically the unity gain frequency is the frequency up to which they are used. So one has to make sure that the zero occurs beyond the unity gain frequency so that the CMRR stays high up to the unity gain frequency. So this is a design challenge, a criterion to make sure that this zero occurs at a high frequency. All right. Okay, let us briefly look. Okay, no. Yeah, so I want to go back to this. I'm sure you remember this circuit, you've studied this a lot in your undergraduate. This circuit is actually ignoring this coupling capacitor. This the RC transistor RECE is the same configuration as this one. This is the equivalent of RC. This is the equivalent of RE. And this is the transistor, and this is the equivalent of C. It's the same topology as the common emitter amplifier. All right. Of course, here the purpose of C is different, but let's think about it. So in this circuit, what we want is that at any frequency of interest, we want to bypass RE so that the gain of this amplifier is large. And how do we achieve that? Why we achieve that by putting a CE. So at low frequencies, very very low frequencies, C is an open circuit. The gain of this circuit is small. It is minus RC by RE. As frequency increases, C starts acting as a short circuit. So the gain of the circuit increases. In this circuit, the CE amplifier, we want the gain to be large at a frequency of interest. So we deliberately make CE very large so that the zero corresponding to CE is at a very low frequency and the gain becomes large at the frequency of interest. In this circuit, it is the opposite. We want the gain to remain small because this is the common mode gain. The common mode gain has to stay small. So we design such that C3 is as small as possible so that the frequency at which the zero occurs is as large as possible. Same circuit, different considerations for design. All right. Okay, let us quickly, one more thing. Okay, so for both the cases we consider the differential mode inputs and the common mode inputs. We made the implicit assumption that the DC voltages at the two input nodes were equal, so that there was complete symmetry in the circuit. Now how about the frequency response of a differential amplifier if the DC voltages at the two inputs of the differential amplifier are not equal? Then of course the currents flowing in the two input transistors will be different. There will be no symmetry, and then finding the frequency response is actually much more complicated because you can't do any symmetry arguments. Such a case is not relevant in any practical circuit because in all practical circuits the input voltages are almost all, well, I would say, unless there is positive feedback, usually there is always negative feedback, and if there is negative feedback, the two inputs of the differential amplifier are always at the same potential, DC potential, and because they are at the same DC potential, our analysis of the differential mode and common mode voltages is valid. So one doesn't encounter this unequal DC input voltages in practical circuits, and therefore this case is never discussed. You won't find a textbook that discusses this case because it is practically irrelevant. Of course, you may encounter such a case in exams because it makes a nice challenging problem to analyze. Okay, the last thing, let's quickly look at the differential amplifier with a mirror load. So we'll just do a very quick qualitative analysis. So as soon as we have a mirror load, there is no symmetry, and we've seen this before when we did the low frequency analysis. From a frequency response perspective, suppose this was not diode connected, there was symmetry, and therefore the time constant at VO1 and time constant at VO2 were equal, and they did not cause two separate poles. Because of the symmetry, it was the same pole on both sides of the half circuit. But as soon as we have a diode connected transistor here, this the circuit is no longer symmetric, and the time constant at this node is different than the time constant at this node, and these cause actually two poles in the overall transfer function rather than one pole. Alright, a current source load has one pole corresponding to the output nodes. A current mirror load diff amp has two poles, and therefore basically the mirror load adds one pole to the overall transfer function. The time constant at this VO2 is the same as the time constant for the current source load, and nothing changes. The time constant at VO1 will be the capacitance, which will be the same at VO2, times the resistance at VO1. The resistance as VO1 is approximately 1 by GM3. It is actually RO1 parallel RO3 parallel 1 by GM3, which is approximately 1 by GM3, which of course is much smaller than RO4 parallel RO2. Therefore, this time constant is smaller than this time constant. So the pole that is added in this mirror load circuit is at a frequency higher than the dominant pole frequency. But overall, the fact that there is one more frequency in the overall transfer function degrades the frequency response. We will see why an additional pole degrades frequency response when we study stability and compensation. All right. So this finishes the frequency response chapter, which was chapter 6 in Razavi's book. Chapter 7 and 8, as I have mentioned before, we are not going to do in this course. 7 is noise, 8 is feedback. We may do this in the next semester in the advanced analog design course. We'll see how that goes. So, but in this course, next lecture, we'll start with chapter 9, which is operational amplifier configurations.